In the previous video, we have seen the theorem of perpendicular axis. Now we'll calculate the moment of inertia along a circular ring. So, there are two things that we consider. The first thing is we can calculate the moment of inertia along a perpendicular axis which is passing from the center of the ring, or we can calculate the moment of inertia along the diameter of the ring, that is the plane of the ring. So first I will calculate the moment of inertia along the perpendicular axis. So first we will consider a uniform circular ring. So let us consider a uniform circular ring. Uniform means all the masses are uniformly distributed all over the length of the ring. Having mass m and radius r. So I am considering a uniform circular ring having mass capital M and radius capital R. So mass per unit length will be mass per unit length. The circumference of this ring will be 2 pi r and mass is capital M. So mass per unit length is capital M upon 2 pi r. You can say it as small m. Now mass for small length is dm, and it is equals to the unit mass into small length dl. So for dl length, this I consider this length is dl. So for this the mass is dm. Now the moment of inertia of this mass, dm mass, along this perpendicular axis, we can find out it easily. How? That the moment of inertia of dm along given axis is I is equals to dm multiplied by capital R square. Mass into distance square from the axis is moment of inertia of a particle, or I can say this so now I I can be written as, from here we can write m dot dl to r square. Now m is a constant quantity and r square is a constant quantity, and now see, if I sum all the small masses to whole ring, then I can find out the moment of inertia of whole ring along this axis. Or this is the moment of inertia for small mass, so I can write here as di. So the integration of di, this sign represents the circular ring. Moment of inertia, integration of whole ring, of moment of inertia of whole ring. So from here I can write m dot dl r square integration. Now m dot dl, so from here I will take out m r square outside and dl inside, and m can be written as from this first equation, m divided by 2 pi r square into r square. Now if I some whole small element of this small ring, of the whole ring, then it can be written as L. And what is L? L is the length of this whole ring, and it is equals to 2 pi r. Sorry, 2 pi r. So from here 2 pi r cancels out, 2 pi r m r square, and this is the moment of inertia of a circular ring along the perpendicular axis. Now we'll see the moment of inertia along the diameter of the ring. Let us take two diameter AB and CD. Let's take two diameter AB and CD which are mutually perpendicular to each other. So because of the symmetry, the moment of inertia along both the axes will be same, or can write because of symmetry of the ring, moment of inertia along AB and CD is same, that is ID. I will take it as a ID. So here we can use the theorem of perpendicular axis for finding out the moment of inertia along the diameter. So from the theorem of perpendicular axis, the moment of inertia along the perpendicular axis is equals to the moment of is equals to the sum of moment of inertia of two mutually perpendicular axes of the ring. So this is the perpendicular axis, moment of inertia along perpendicular axis, and the sum of moment of inertia along the diameter is this. So from here we know that the moment of inertia along the perpendicular axis is mr square, and id plus id is 2id. So from here id is equals to mr square by 2. So for perpendicular axis, moment of inertia is mr square, and for diameter it is mr square by 2.